So this is the last technical topic in 6034. You're almost there. We're going to talk about boosting, and specifically Adaboost, which is a type of boosting, which we saw in lecture this morning. So the general idea here is we're combining together all of the different machine learning methods that we saw earlier in the semester to be able to make a strong classifier by using all of the information. So what are some machine learning methods we saw? What's one machine learning method we've looked at? Nearest neighbors. Okay, so we can make a list of machine learning methods. We have different flavors of nearest neighbors. Like we have one nearest neighbor. We could do 3 nearest neighbors or 5 nearest neighbors. We could use different distance metrics. What else have we looked at? SVMs. Okay. What else? Neural nets. I think we have 2 more.
ID trees.
Yeah, ID trees. And today in lecture we use just ID tree stumps, the first level of an ID tree, which we'll also do today. What did we see last week? Was there any machine learning last week? It's too long ago. So we looked at naive Bayes classification, which is yet another type of machine learning. We're going to say that all of these are weak classifiers. In our classroom examples, they generally classify our training data perfectly because we only have like 5 to 10 data points. But in a real data set where you have dozens of features and hundreds of training points, it's going to be difficult to classify everything correctly. So we'll say that these things are weak or imperfect classifiers. And we'll call them little h sub I. Then what we're going to do is we'll combine them all together, or combine some subset of them to form some strong overall classifier, big H of x. So this is sometimes called an ensemble classifier or aggregate classifier because it's just combining together all of the weak classifiers. This is just like any other machine learning rule where it takes in a vector of features and it returns a classification. In this case, it's a Boolean classification. It'll be +1 or -1. So our rule will be that's equal to the sign of a vote of all of the weak classifiers. So we'll give each weak classifier some voting power that we'll call alpha. These alphas are completely different from the alphas in support vector machines, which were supportiveness. These ones are voting power. We're just reusing the same letter. So we might have some voting power times the first weak classifier plus some voting power alpha 2 for the second weak classifier. And we'll keep doing that until we've added enough weak classifiers that we can get a good classification out of our overall classifier. So we'll go up to alpha n hn. So now the question is just how do we build this classifier? How do we choose the classifiers and determine our voting powers? So in the big picture, we're going to have an error rate for each of these weak classifiers. So we can say each weak classifier, little h, will have some error rate that we'll call epsilon. That error rate is going to go between 0 and 1, where here's the error rate. 0 means that it classifies everything perfectly correctly, and 1 means it classifies everything completely wrong. So if it classifies more things correctly, would we want it to have a higher or lower voting power? Higher. Makes sense. So we'll give it more voting power in this direction. But if our classifier classifies everything wrong all the time, and there are only 2 classes, is there some way we could make use of that?
Do the opposite.
Yeah, do the opposite. There we go. So we can also say that they can have more voting power as they become more wrong. We'll just give them more negative voting power. So we'll take their vote into account and then just do the opposite of whatever they say. We have more negative voting power there. That means over here we have more positive voting power if they're more correct. And in the middle we'll have less voting power. The middle being an error rate of 1/2. Okay, so each classifier has an error rate. And now the way we're going to assemble this overall classifier is in a series of rounds. So our overall classifier, big H of x, is assembled in a series of rounds. And in each round, we're going to do a few things. We're going to pick the best weak classifier to add to our overall classifier. I'm going to put best in quotes because we haven't defined that yet. I'll pick the best weak classifier, little h. And then we'll assign that classifier a voting power. That we'll call alpha for that weak classifier, a voting power. And finally, we'll just append that onto our overall classifier. So we'll append the term alpha h of x to our overall classifier, big H of x. So now there's this question of what does it mean to be the best? So we're going to say best means a couple things. It's going to mean the classifier that makes the fewest errors, or in this case, the most errors. But for now, we'll keep it simple and just say the fewest errors. But we're also going to weight that so that we emphasize the points that have been misclassified in previous rounds. And that's where the actual power of boosting comes in, because if the weak classifiers we've chosen so far make certain mistakes, we want to correct for those in the next classifiers we choose. So this will be adjusted to emphasize points that were previously misclassified. So that's the general idea of boosting. And now we're going to figure out how this actually works mathematically using some of the formulas we derived in lecture. So we're going to start building a flowchart, and we're going to do an example problem. So we can start with the example problem over here. We're going to have just 5 data points. This is a classroom example. We'll have 4 plus points and 1 minus point. We'll label them A, B, C, D, and E. Their x-coordinates are 1, 3, and 5. And their y-coordinates are also 1, 3, and 5. This is x, and that's y. And then in this particular problem, which is from 2012 quiz 4, we're going to be allowed to use 6 classifiers. So we're just going to use decision tree stumps, and in this case they'll all be vertical lines. So our classifiers will be x less than 2 x less than 4, x less than 6, and then the opposite of those, x greater than 2, x greater than 4, and x greater than 6. And so what these mean, for example, x less than 2 is going to mean we'll draw the line x equals 2, and everything that's on the left side of the line, everything that's less than x, will be classified as a plus. Everything else will be classified as a minus. So which points does x less than 2 misclassify? If it says everything to the left is a plus. B and E, yeah, because it says B, C, and E are minuses, and B and E are wrong. So we're going to make a list of misclassified points. And here we'll have B and E. What about x less than 4? That will draw the next line over, which will be there. So that says that A, C, and D are pluses, B and E are minuses. What's wrong?
C, B, and E.
Yeah, C, B, and E. And then x less than 6 just says that everything is a plus. So that's going to misclassify point C. What about x greater than 2? That says everything to the right of the x equals 2 line is a plus.
A, C, D.
Yeah, A, C, and D. So we can notice that's actually the opposite of what x less than 2 misclassified, which makes sense because we just inverted the classification. So we can also do x greater than 4 will be the opposite of x less than 4, and we'll have A and D. X greater than 6 is the opposite of x less than 6, and we'll misclassify A, B, D, and E. Okay, so now we can get to the first thing in our flowchart, which will be assigning weights to each of these training points. So we're going to initialize the weights to all be equal because there's no reason right now to emphasize one training point or another. So we'll initialize weights and we'll set the weight of each training point to be 1 over the total number of training points so that the weights will add to 1. So in other words, we're assigning each training point an equal weight. So what should be the weight of training point A? How many training points do we have? 5. So what should be the weight of each point? Yeah, 1 over 5. So we're going to turn this into a table where we'll have the weight of each training point, the weight of A, weight of B, C, D, and E. And right now they'll all be 1 over 5. So we said boosting is going to happen in rounds. So this is round 1. Okay, we have a weight for each training point. Now what we're going to do is compute the error rate for each of our weak classifiers. So our next step is calculate error rate for each weak classifier, little h. The error rate will just be the sum of the weights of all of the points that classifier misclassifies. So the sum of weights of everything that it gets wrong. So what would be the error rate for x less than 2, which misclassifies b and e? 2/5, because we're just adding the weight of b plus the weight of e, and we get 2/5. So it's a little messy. So if we put the error rate for each of these here, the error rate of x less than 2, we just said, will be 2/5. And so that's, in this case, in the first round, the error rate will just be the fraction of points that are misclassified, because all the points have equal weight. So what would be the error rate for x less than 4? 3/5, because it misclassifies 3 points. And then we'll get 1/5 for x less than 6, which misclassifies c. We'll have 3/5 for x greater than 2, 2/5, and 4/5. One thing we can notice is the error rate of the greater than classifier is just 1 minus the error rate of the less than classifier, which makes sense because they just do the opposite thing. Okay, so now we have error rates. Now we need to choose which of these classifiers is the best. So for now, we're going to ignore the fact that we can use classifiers that are mostly wrong, and we'll just look at the one that has the smallest error rate, makes the least errors. So we'll pick the weak classifier that has the lowest error rate, or the smallest error rate. We'll pick the best weak classifier. That has the smallest error rate. So which one is the best right now by that definition?
Less than 6.
Yeah, x less than 6, because it has an error rate of 1/5, which is less than any of the others. So we'll pick that one. We'll extend our table a little more and keep track of the best weak classifier in each round, its error rate, and its voting power. So our best weak classifier is x less than 6, we just said. Its error rate is 1/5. Now we just need a formula for the voting power. So this comes out of the formulas we saw in lecture. We won't actually derive it right now, but you can derive it at home if you want. So we'll calculate voting power. For our best weak classifier. And the voting power will be defined as 1/2 the natural log of 1 minus the error rate over the error rate. So if our error rate is 1/5, then this will be 1/2 the natural log of 1 minus 1/5 over 1/5, which is equal to 1/2 the natural log of 4/5 over 1/5, which is 1/2 the natural log of 4. And for now, we don't actually care what the natural log of 4 is, but this is going to be some number, which is our voting power. So here we'll put 1/2 the natural log of 4. And then we'll just append that to our overall classifier. So if we build an overall classifier over here, we'll have our big H of x will be the sine of a bunch of terms. What's the first voting power?
1/2 log 4.
Yeah, the thing we just calculated, 1/2 the natural log of 4. And what's the weak classifier?
Less than 6.
X less than 6. So just as a shorthand, I'm going to put x less than 6 here. Really, we need this to be a function that returns +1 or -1 depending on the features you give it, but this will just be shorthand for whatever decision is returned by that classifier. So this term would be plus or minus 1. So now we need to know whether we're done. So we're going to ask, are we finished? There are a few ways that we can be finished. The first one is if our overall classifier, big H, is good enough. So good enough is, it depends on your goal. In general, that'll be given. It could be something like for a large data set, I want 90% classification accuracy. In this case, because we only have 5 points, let's say good enough is, it's only good enough if it perfectly classifies all of our training data. So is our big H good enough? No, because it misclassifies point C because it's only using x less than 6 currently. So it's not good enough. There are 2 more criteria though. One is if we've done enough rounds. This is another criteria that has to be given to you. In this case, let's say we'll do this for at most 4 rounds, and if we haven't reached one of the other termination criteria by then, we'll stop. So have we done enough rounds? No, because we did 1. And then the last criteria is if there are no good classifiers left. This one is a little more well-defined. We're going to define this as if our best classifier, if our best weak classifier has an error rate of 1/2, we're going to say there are no good classifiers left. So if our best weak classifier H has error rate of 1/2. So that one we don't actually know until we look at the error rates for our weak classifiers. So in our first round, we still had good classifiers left, and when we get to when we recalculate our error rates, then we'll have to ask the question again. So for now, it looks like we're not done. But if we were done, then we would just return our overall classifier. If we're not done, we're going to update the weights of the points and go on to the next round. So update the weight for each training point. And specifically, we'll do that to emphasize the points that were misclassified in the previous round. So we'll have a weight update formula for this, and it'll depend on whether the point was classified correctly or incorrectly. So if the point was classified correctly, the new weight will be 1/2 times 1 over 1 minus the error rate times the old weight. That's if it was classified correctly or classified right. Otherwise, it'll be 1/2 times 1 over the error rate times the old weight. That's if it was classified wrong. If a point was classified wrong, do we want its weight to go up or down? Up, because we want to emphasize that point. And so that means that because we want all of our weights to always add to 1, if the points were classified right, their weights will need to go down. So we could add that to our diagram over here. The fact that our weights, if the weight was, well, our new weight, if the point was correct, will increase and our new weight if the point was classified incorrectly or wrong. Oops, I did that backward. That one will decrease. And if it was wrong, then the weight will increase to emphasize that point. Okay, so let's try recalculating our weights for round 2. So if we recalculate weight A, we'll have 1/2 times 1 over 1 minus, what's our error rate? Which error rate are we using? Yeah, 1/5. So that's going to be the error rate of our weak classifier that we just tried. And what's the old weight of point A? Yeah, 1/5, because all of our old weights were 1/5. So times 1/5. So that's going to be equal to 1/2 times 5 over 4 times 1 over 5. Those cancel, and we get 1 over 8. What will be the new weight for point B? Yeah, it's the same. Because the 1/2 doesn't change, the error rate is the same, and it had the same old weight as point A, so it'll also have a new weight of 1/8. And then similarly, D and E were classified correctly, so they'll have an error rate of 1/8. But point C was classified wrong in the previous round. We'll mark that. So if we calculate the new weight for point C, we'll have 1/2 times 1 over 1/5 times 1/5. These 1/5s will cancel, and we get just 1/2. There's another way we could have figured that out, though. We learned in lecture today that all of the weights should add up to 1 in every round. So because C was the only point left, we could have just looked at A, B, D, and E, saw that they added to 1/2, and that would give us weight C must be 1/2. So that's actually a general fact, that the weights of all of the points that were classified correctly in the last round will always add up to 1/2. And accordingly, the weights of the points that were classified wrong in the last round will also add up to 1/2. So sum of the weights that were classified right is equal to the sum of the weights that were classified wrong, which is equal to 1/2. And that also leads to the fact that the sum of all of the weights is 1. So that means that we could actually use this to update our weights intuitively instead of using these weight update formulas. We could just look at the weights and see A, B, D, and E were in a ratio of 1 to 1 to 1 to 1. And we know that their new weights will be in the same ratio because of the formula, because the old weight is the only thing that changes. And we know that their new weights have to add up to 1/2. So from that we could deduce that they must all be 1/8. So we'll try that in the next round and see how it works without calculating weights using formulas. Okay, so now we've updated our weights. Now we're going to go back to some step. Which step should we go back to? What do we need to do next?
Calculate the error rate.
Yeah, we need to calculate our new error rates. So there isn't much space for this, but this is going to go all the way back to there to calculate new error rates. So what's the new error rate for x less than 2, which misclassifies B and E? How do we calculate that? Yeah, we'll just add up some weights of points. So it misclassifies B and E, which each have an error rate of 1/8, so we'll get 2 over 8. I'm going to rewrite C as 4 over 8 to make it easier to add up these fractions. And then we can say x less than 4 misclassifies B, C, and E. So its error rate will now be 1/8 plus 4/8 plus 1/8 is 6/8. X less than 6 just misclassifies point C, so that will be an error rate of 4/8 or 1/2. That's a useful fact that whichever classifier you just used will always have an error rate of 1/2 in the next round. And the reason why is the error rate is just the sum of all of the points that classifier misclassifies. And that's the classifier we just used. So we just said that the points that were misclassified by it in the previous round should now have weights that add up to 1/2. So by definition, that new error rate is going to be 1/2. Does that make sense? Okay. Okay, what about x greater than 2? We can use the fact that x less than 2 and x greater than 2 are opposite, so we just get 1 minus 2/8 is 6/8. Here we'll have 2/8 and then 4/8 or 1/2. So which classifier is the best? Yeah, we have a tie. So we'll need a tie-breaking rule. Let's say that our tie-breaking rule is we'll choose classifiers that appear earlier in the list first. So which one should we choose? Well, yeah, the first one, because our lowest error rate is 2/8, so we have a tie. So we'll choose the first one. So we'll get x less than 2 with an error rate of 1/4. And then if we calculate this voting power, we now have an error rate of 1/4, so this would be 1 minus 1/4 over 1/4. This becomes, oh, that's messy. This becomes 1/2 the natural log of, let's see, 3/4 over 1/4, which is 1/2 the natural log of 3. So there's actually a pattern here where when our error rate is 1 over some number n, our voting power is just 1/2 the natural log of n minus 1. So we can use that if we keep getting error rates of 1 over something, so we don't have to keep calculating it. Okay, so we'll add that onto our overall classifier. We have now 1/2 the natural log of 3 times the decision made by x less than 2. Are we done? Is this classifier good enough? So what happens if we have exactly 2 weak classifiers that are voting, and one of them has a higher voting power? If they disagree on something, who will win that vote? Yeah, the one with the higher voting power. So this means that whenever they disagree, like they're going to disagree on point C, the first one is going to win because log 4 is bigger than log 5. So this is basically the same as the classifier we had before because that first one always wins. So is H good enough? No, it's not good enough yet because it's still going to misclassify point C. Okay, have we done enough rounds? No, we said we want to do 4 rounds. And it looks like we did have a good classifier because our best classifier had an error rate that wasn't 1/2. So we'll keep going and we'll update the weights. So which points were misclassified in round 2? So this is a little tricky because our overall classifier, yeah, it only misclassified C. But when we're updating the weights, the points that we're considering are the ones that were misclassified by the most recent weak classifier. So we're going to say that x less than 2 misclassified B and E. So those are the points whose weights we're going to increase in the next round. And the reason why we're not just looking at C is because even though C still isn't classified correctly by our overall classifier, the classifier we just chose did classify it correctly, and we've already taken into account our first classifier not being very good for C. So we're not going to double count that. So given that B and E were misclassified in the previous round, their weights are currently in a ratio of 1 to 1, and their new weights have to add up to 1/2. What will be their new weights? A quarter, yeah. So 1/4 and 1/4. A, C, and D will be a little trickier. We see that they're in a ratio of 1 to 4 to 1, and their new weights have to add up to 1/2. So what could one of those weights be? Almost. So one way to think about this, so for some people it might be easier to just use the weight update formulas. You could use the weight update formula to get one of them and then scale it to get the others. But if you want to do this just intuitively, the way I like to think about it is if we have a ratio of 1 to 4 to 1, those add up to 6. So our denominator has to be some multiple of 6. And we want the sum of those three to be 1/2, so we'll do 1/6 times 1/2 gives us a denominator of 12. So if we do 1/12, 4/12, and 1/12, those add up to 6/12, which is 1/2. So we're good there. Okay, and then we can rewrite all of these guys in 12ths, so these are 3/12, and then they'll be easier to add up. So now what's the error rate for, well, what's the error rate of a classifier we just used? X less than 2. 1/4, where does that come from?
The error rate we calculated for X less than 2.
Oh, so that's the error rate that it had. But what will its new error rate be? So its new error rate is going to be the sum of the weights of the points that it misclassifies. And we know that the weights of B and E, we said, had to add up to 1/2. So what's this error rate? 1/2. So that's again this property that the classifier you just used will always have an error rate of 1/2 in the next round. And then for X less than 4, we'll have to add up B, C, and E. So it's 3/12 plus 4/12 plus 3/12 gives us 10/12. Point C is just 4/12. So this error rate stopped being 1/2. And then X greater than 2, well, we can do 1 minus what we got for the less than classifier. So we have 1/2, 2/12, and 8/12. So what's the best classifier?
X greater than 4.
X greater than 4, yeah. So 2/12 is the lowest error rate, which means that X greater than 4 is our best classifier. So that has an error rate of 1/6. So if we follow this pattern, our voting power will be 1/2 the natural log of 6 minus 1 is 5. And you could also calculate that and you'd get the same value. So we'll add that to our overall classifier. 1/2 the natural log of 5 times the decision made by X greater than 4. Now is our overall classifier good enough?
Yeah.
Yeah, it is. And here's how we can find out. If we just look at which points each of these misclassifies, we said that X less than 6 misclassifies C. X less than 2 misclassifies, what is that, B and E? And X greater than 4 misclassifies A and D. So that means that for each of the training points, only one classifier is wrong about it. So that means that as long as the two that are right can add up their voting powers and overpower the one that was wrong, then they'll classify everything correctly. So that just means that we need these 3 voting powers to satisfy the triangle inequality where any 2 of them added together is greater than the third. So the smallest ones are 1/2 log 3 and 1/2 log 4. Is that greater than 1/2 log 5? How do you add logs?
Multiply the inside.
Yeah, multiply the inside. So if we want to do 1/2 the natural log of 3 plus 1/2 the natural log of 4, that will just be 1/2 the natural log of 3 times 4. So is the natural log of 12 greater than the natural log of 5? Yeah, because the log of a bigger number will be a larger number. So is h perfect now? Who thinks we're done? Who thinks we're not done? You think we're done? Okay, no one else wanted to vote, so yeah, we're done. This is human boosting. So the reason why we're done is because each point is misclassified by only one classifier, and the other two can always overpower the one that's wrong. So we got h is good enough. We don't need to keep going because we only need one of these criteria to be true. So now let's see what would have happened if we had allowed classifiers that made lots of mistakes and given them negative voting power. So we could amend this thing that says the smallest error rate. And we could say, well, what's even better than using smallest error rate is using the error rate that's furthest from 1/2. Because if it's almost always wrong, then that's also useful. So even better is furthest from 1/2, which mathematically is whichever classifier has the largest value, the largest absolute value of the error rate minus 1/2. So that's just whichever one has error rate furthest from 1/2. So if we use that criteria, which classifier would be the best in our first round? Is it still x less than 6? Is there anything that's better or just as good?
The last one.
The last one? Yeah, so 4/5 is just as far from 1/2 as 1/5. It's just in the opposite direction. So in this case, our tie-breaking rule would pick the 1/5 over the 4/5, but they would be equally good. And then what about in the next round? Is there anything better than or just as good as 2/8? Yeah, 6/8 is just as good. So in this case, we would actually have 4 classifiers that are tied for being equally good because they're equally far from 1/2. But our tie-breaking rule would again pick the first one. What about in the third round?
We use less than 4.
Yeah, so 10/12 and 2/12 are equally far from 1/2, but x less than 4 comes first. So we would pick x less than 4 with 10/12. So this would become x less than 4. We would have an error rate of 5/6. And if we do the math, we would end up with a voting power of 1/2 the natural log of 1/5. Or what's another way we could write that? Yeah, so that's the same. This comes out to the same as
Just 5.
it's negative 1/2 the natural log of 5. And so that makes sense because we chose, instead of x greater than 4, we chose the opposite classifier, x less than 4. So it makes sense that we would give it the same voting power, just negate it. So over here we would have plus, or instead of a minus, 1/2 the natural log of 5 times the decision made by x less than 4. And so in this case, this would make the same overall decision as if we used a positive voting power with x greater than 4. And as for which criteria to use, this one is better, but on a quiz you would be told whether you should use furthest from 1/2 or just absolute smallest error rate. So a couple other things we can see with regard to this is, well, what would happen if we had an error rate of 1/2? What would be our voting power? We can calculate that. If we have an error rate of 1/2, then this is the natural log of 1 minus 1/2, which is 1/2 over 1/2. What's the natural log of 1? 0. So this isn't just less voting power. This is, if we did choose a classifier with an error rate of 1/2, our voting power would be 0. So that's one reason it's silly to choose a classifier with an error rate of 1/2. But then another question is, well, maybe we would then update the weights and it would get better. So let's see what would happen if we update the weights with an error rate of 1/2. We would have here 1/2 times 1/1/2.
Well, we would never get there, would we? We would stop at
We wouldn't, but this is if we were to keep going. I'm going to show why you wouldn't want to keep going. So if we had 1/2 times 1/1/2, those would cancel out, and you would just get the new weight is equal to the old weight. And you would get the same thing here. So not only would you end up adding a classifier with 0 voting power, which doesn't do anything, but you would also update the weights to be exactly the same as the old weights, so you would just be stuck in an infinite loop of adding useless classifiers. So that's why we're going to stop if our best classifier has an error rate of 1/2. So we can say here in the middle, the new weight would be equal to the old weight, even though we'll never actually choose that case. And then as we go this way, we said if the point was classified correctly, its new weight will decrease. If it was classified wrong, its new weight will increase. What about as we get closer to negative? If we have more negative voting power and we have an error rate closer to 1, would we get the same behavior?
No, the exact opposite.
Yeah, it's going to be exactly opposite. And the reason why is x less than 4 says that it misclassifies B, C, E. But because we're negating its decision, it's effectively misclassifying A and D. So in this case, it would say, oh, but B, C, and E are classified wrong. But effectively, they're classified right, so we want their new weights to decrease. OK, let's look at a couple other neat facts related to boosting. Are there any questions first? OK. Let's see. Oh, I guess we can just fit these in here. So one thing is the weights are always going to be greater than 0, the weight of each training point, and less than or equal to 1/2. And that's because in the first round we start off with equal weights for all the points. And then when we update them, each point was either classified right or wrong. And each of those sums is 1/2, so no one weight can ever be greater than 1/2. The only exception to these rules is our weird trivial pathological cases where you have exactly one training point or you have a perfect weak classifier, in which case there's no reason to be doing boosting. But in general, these facts will hold. A consequence of these up-down arrows is a new weight. The new weight of a point will never be equal to its most recent weight. So the weight of a point will always change from one round to another, because the only way for it to not change is to have an error rate of 1/2, which we'll never choose. Another consequence of this is if we think about what happens to an outlier or noise point, most of the classifiers will classify it wrong, so its weight is going to continue increasing and increasing until eventually it gets classified correctly or we stop before then. So one way to think about that is this boosting system is becoming more and more anxious about this outlier point that never gets classified correctly until eventually it does get classified correctly.
Isn't that kind of bad, though?
Like in terms of overfitting?
Yeah.
Well, so we saw that in lecture today in one of the examples where there was some noise point, and there were, I think it was the rings of Saturn. Then there was some noise point, and eventually it just ended up with this very small area dedicated to it. So you could say that that's overfitting, but it overfits a lot less than most classifiers because it's going to ignore that point for a long time until that's the only thing left that it can fix. So in general, boosting does help a lot with overfitting. And you could also do something like choosing a good enough threshold to be, I want to classify 95% of my training data. And then you would ignore that outlier. Two other neat things. Let's see. One is if you have 3 or more disjoint classifiers, that is classifiers that make non-overlapping errors, which we had in this case, then you're guaranteed to be able to make a perfect classifier out of them. So for example, if we had 3 classifiers, H1, H2, H3, and H1 misclassified A, B, C, H2 misclassified D and E, and H3 misclassified F and G, then it's definitely possible to just assign each of these equal voting power and you're guaranteed to get a perfect classifier. But one thing to note is that it's not guaranteed that boosting will choose those 3 classifiers in the first 3 rounds, just that as a human it would be possible to construct a classifier. Another thing to note there is the converse is not true. So just because classifiers make overlapping errors, like if you have some other classifier, H4, that misclassifies C and D, and if, well, that's not a good example, but because classifiers make overlapping errors doesn't necessarily mean that you can't make a perfect classifier out of them. And then one other thing is if a classifier makes a superset of errors that other classifiers make. So like here we said x less than 4 misclassifies B, C, E, whereas x less than 2 misclassifies B and E. Then it's guaranteed that that classifier will never have the smallest error rate. And the reason why is the error rate of x less than 2 is the weight of B plus the weight of E. X less than 4 is those weights plus the weight of C. And the weights will always be greater than 0. So that means that if it misclassifies all the points that x less than 2 misclassifies and then some, it'll always have a bigger error rate. And so, yeah.
If we're using the absolute value, then in that case it would still be.
Yeah, well, so it will never have the smallest error rate, but you might still use it if you're using that, yeah. I think that's everything. Let's see. Yeah, so that's basically everything you need to know about boosting. And so that's basically everything you need to know in 6034. Have a great Thanksgiving.